Hello everyone, my name is Christelle Habis, a PhD student at the Université de Lorraine, and in this contribution I will be presenting the effect of spraying distance on the morphology of zinc oxide thin films deposited by sputtering. As an outline for this presentation, the first part is an introduction about transparent conductive oxides, which are also called TCO, in which I will highlight their importance, electrical and optical properties that will define a figure of merit to be explained. Then in the second part, I will explain the elaboration method of ZNO thin film along with the characterization technique for surface morphology investigation. Finally, I will end up by findings and discussions. The discovery of TCOs dates back more than 100 years ago, and ever since the value of these materials keeps growing commercially. The importance of TCO relies in their unique property of optical transmission combined with electrical conductivity. They are usually N-type semiconductors with a band gap that is higher than 3 electron volts. And the most important binary oxides are indium oxide, zinc oxide, and tin oxide. They have a multitude of applications like energy harvesting applications as well as detectors. Generally, the TCO are resistive at room temperature, since they are semiconductors with a wide band gap. So in order to become conductive, external impurities are introduced into the film. And the conductivity is related to microscopic parameters describing the motion of electrons as seen in this equation. According to this, we have two ways to increase the conductivity. The first way is by improving the carrier concentration, hence the doping concentration, and a second way is by improving the electron mobility. But we have some limitations since heavy doping can have disadvantages such as acting as scattering centers and then reducing electron mobility and decreasing the light transmission. As said earlier, doping these oxides render higher conductivity. But let's see what really happens inside the energy bands. So when doped, the lowest state of the conduction band becomes partially filled. So the photon need higher energy to excite transitions from valence to conduction band. So the transmission decreases. Doping increases the conductivity, but it also has an impact on the transparency of the film. So a compromise between conductivity and transparency needs to be found. This compromise is defined as the figure of merit, FOM, which is equal to the ratio of conductivity to the absorption coefficient. As example, the table illustrated here shows a figure of merit for some TCOs as stated in literature. It ranges from the value of 7 down to 0.2 for some, depending on the material. Zinc oxide is a well-known and extensively studied material because it has so many properties that made it the material of choice for many applications. ZNO, it crystallizes in Wurtzit form and has high transparency in the visible spectrum, high electron mobility and thermal conductivity, and a wide band gap of 3.37 electron volts approximately. In addition to being a low-cost, abundant, and non-toxic material, it also has remarkable electrochemical, thermal, and mechanical stability. The properties of ZNO could be easily enhanced by doping, and many deposition techniques are suitable for ZNO deposition, such as magnetron sputtering, electron beam evaporation, spin coating, dip coating, spray pyrolysis, pulsed laser deposition, and many more. The film was grown by a sputtering method at Institut Jean Lamour, Nancy. The sputtering technique could be described briefly by the bombardment of a target plate with energetic ions. Upon condensation, these ions form a thin film on the substrate, as shown in the scheme here. 3 regions were identified on the substrate and labeled as B1, B2, and B3. The deposition parameters are summarized in the following table, and the characterization of the sample was carried out by atomic force microscopy AFM, where the main purpose was to visualize the surface morphology and evaluate the relation between film thickness and grain size. So the characterization was carried by AFM, which is an imaging technique that permits the visualization of the sample surface topography. It provides high-resolution pictures of surface atoms, and it is a non-destructive technique since no previous treatment is needed for the samples. The surfaces of the film reveal the presence of high peaks and deep valleys in the same wafer. Close to the center of the sample's holder, it means in the position of 4.5 centimeters of the direct sputtering jet, which is at the zone B1, the peak valley distance is in the order of 20 nanometers, while at a distance of 7.5 centimeters, which is the B3 zone, this distance decreases down to 10 nanometers. This morphology of the surface of ZNO layer could contribute in the increase of its roughness. However, the plot of grain sizes along with the thickness of the film as a function of the distance from the holder's center shows an increase in the grain size with distance, as well as a linear increase in the thickness of the film. In addition, also the grain shape was reformed. They transformed from spherical to pyramidal shapes, as shown in the pictures of the surface. It is well known that the morphology of the surface of a TCO layer has an important role in improving the light scattering and thus the energy conversion efficiency by increasing the light path length through reflection and scattering of the incident light. Finally, as we have shown, the spray distance has a direct influence on the morphology. Also, it is useful to mention that it has an indirect influence on the haze factor of the TCO layer that will increase as the spray distance increases. And furthermore, we have seen that the thickness of the layer also increased. This will have a direct impact on the absorption of the layer. So in the end, we found that the distance from the center has an effect on the morphology of the film, and that grain size and shape are closely related to the film thickness. And we can conclude that controlled texture is beneficial for improving the haze factor for specific applications. Thank you for your attention, and I can answer your questions.